All right. Hello, everyone. Let me raise my volume here. Okay. So we have started the recording, or basically I have started the recording, but before I start the recording, I just wanted to make this quick announcement just to show that for next Tuesday, we are already going to be going through 4.1. 4.4. We will be squeezing in a review on the 23rd and then taking the exam by the end of the month. The other thing that I wanted to mention, and I had mentioned previously, but I did not have time to include it and or I forgot, is the fact that there are two sheets up there. It is the quadratic functions sheet, and it is the completing the square. There are two sheets up there in the chapter 3 folder. They are blank, okay? Do not stress out. I have them also filled out. So like I said, you can fill them out yourself just to kind of get some practice on, or maybe write it in your own words. Maybe my words are difficult to understand. Maybe you want to write it differently. I don't know. You can use the one that I have up there, which is basically this one. I already have it filled out, pre-filled out, so you can use that on the exam. You don't have to waste time, space, or energy in rewriting it on your note card for next chapter test. And then over here, you can also use this. And this one's also pre-filled out. You can do as you wish with it. You can definitely use it on the exam, okay? So, yes. So as you go through Unit 3, Unit 4 will also have some of this information. And so what you want to be able to do is understand what this means and how this works, okay? So that's for chapter 3. All right, let's start with chapter 4. I also wanted to state that chapter 3 review is up there, ready to go. We can definitely do that on the review date, which is the 26th. I believe it's 26th, is it? It's on the 23rd. Sorry, it's on the 23rd. The exam is on the 30th. So by the time I see you on the 23rd, you should have gone through all those sections. There's 8 of them total. All your homework should be finished in order for you to come here with questions regarding Unit 3 and 4 for your exam on Units 3 and 4. All right, let me go over 4.1. Let me get this out of the way. All right, 4.1 and 4.2 is what I'm going to be doing today. Let me move this up. Okay, and let me stop it from auto-focusing. Okay, so the graphing of the polynomials are just basically curves that are just going to go on forever and ever and ever. They don't have any asymptotes, as you will see in the next chapters. Asymptotes are any vertical lines or horizontal lines or even diagonal lines that make this beautiful curve go a different way, right? So when you are looking at polynomial functions are written in this format. Now, do not look puzzled by the complication of this equation. It just basically means that you are going to normally 99% of the time, let's say 99.99999% of the time, you're going to want to write these in descending order. So the highest power goes first and it decreases all the way to the constant. In math, because obviously the alphabet is limited, we don't want to put A, B, C as the constants because there is a limited number of alphabet letters. So what we do is we choose a letter, A, and then we just change the subscript. So because we know numbers are infinite, we can choose a subscript like the letter N, which could be anything. It could be a 1 or 2. So it just means subscript 1, subscript 2, subscript 3, all the way to the very last term that has a subscript that has no variable, which is called a constant. So there are a couple of important definitions that you should know that maybe you should start writing as you go through the lessons. My suggestion to you is to, as you start going through the media, as you start going through my videos, you start taking notes on important definitions, okay? Because the questions that you are going to be asked have these definitions. And if you don't know the definition of something, there is no way that you're going to be able to answer it. And it's just pointless, right? You can't answer the question because you don't know what it's asking. All right, so n is basically the degree. We're going to give it the name degree. So that would be this little number right here. Okay, the degree of any function is the highest power. Okay, so even if it's out of order, you don't look at the first one, you look at the highest power. The next thing is the leading coefficient, a sub n, and instead of writing the whole word leading coefficient, I'm just going to put LC. Leading coefficient is the number next to that highest power. So it's just a number, could be positive, negative. It's a number next to the variable with the highest power. Okay, and everything is okay. And the last one is the constant. The constant is just a number without a variable. End of story. That's it. All right. A sub I is a real number where a sub n is not equal to 0 and n is a whole number. So it just means that these parts are coefficients until you finish ordering everything from small to big. All right. So that was a long intro to polynomial functions. All right. So polynomial functions are given certain names. Okay. But after the fourth, maybe fifth one, they stopped giving them names because otherwise there would be names to infinity and there can't be a whole bunch of names to infinity. That would just be a lot of names to memorize. So the basic ones are the following. Let me do this. Okay, so the common polynomials are what you would see here, what you saw already on unit 2. Okay. Yeah, unit 1 and 2, basically 1 and 2. And it's what we have as a line. So this is the equation of a line. It's called slope-intercept form. It is a degree of 1 because the highest power on the variable is a 1. A and B are numbers. So this is called a linear equation, and it is a degree of 1. When you're looking at degrees, you want to state whether, obviously, the number, so the highest power, whatever that is, and you want to state if it's even or odd. So in this case, it is odd, okay, because it's a 1, obviously. And so I have it on the left side, even odd, and I circled odd, and I just rewrote it over here, okay? All right, the next one is what you've seen a little bit in chapter 2, but you've seen more in chapter 3. This is called a quadratic, where the highest power is a 2. That 2 is clearly even. And so you would write down quadratic as its name. It's a degree of 2, and it's even. Okay. All right, if the highest power is a 3, it doesn't matter what order these are, but if the highest power is a 3, obviously 3 is an odd number, it's called a cubic, and it is an odd degree. If the highest power is a 4, it is obviously even, it's called quartic, and it is an even degree. And that is all the names that you need to know. Those are all the names that you need to know. Okay. The bottom is basically what you're going to see in terms of what they look like. So when you are asked to make a typical equation of a 4th degree or a 3rd degree of whatever, you know exactly where the endpoints go. You're going to be working with end behavior, and end behavior literally means the end arrows. So there could be going opposite, like that. Okay, they could be both going up, or they could be both going down. There's only 4 options. And this is what we see here. All right, so if the degree, basically, if the degree is odd, so you always start with odd. You want to think, okay, a line is an odd, a quadratic is an even. So just go based off that. So if you have understood that lines are odds, and when you have positive slopes, they go this way. And when you have lines that are negative, go this way, they come down. That's basically how every single odd is going to be similar. Okay, so they just might not be a straight line. They might have more curves in the middle, but the fact is that the arrows will always point the same way. So if you have an odd degree where the leading coefficient that is positive, you will have your arrows go that way. One down, one up, because it's going to simulate a positive slope. If you have an odd degree function that has a negative leading coefficient, it's going to be going down that way. Okay, so it's going to be coming down basically as a negative line with the slope that's negative. If you are thinking about even degrees, you want to think of parabolas. So they're either happy faces if they have a positive coefficient, or they're negative. So they're facing downward if they're negative. And so any even degree function, whether it's a 2, a 4, a 6, an 8, any even will have these two lines go up if they have a positive leading coefficient. In the middle, you might have more curves. You have more or less curves, it doesn't matter, but the end arrows are going to both face up. And it is also true that if you have a degree that is even with the leading coefficient that is negative, it's also going to behave like a parabola that got flipped upside down. Therefore, the arrows will go down. And so this is where we encounter then the end behavior, which you're going to do in a minute. But if you can understand these, just relate every odd to a line and every even to a parabola, then you'll be fine. All right. So the end behavior, and I know it looks kind of like a mess here. It actually looks like a mess, not kind of, but it really does. Okay. It says for the end behavior, there are two sentences depending on the signs. So, and they depend on the signs. So over here, if you have an odd positive, so an odd degree with a positive leading coefficient is going to do something like that. This arrow is going to be in quadrant 1, where every point in that quadrant is positive, positive. Every point in this arrow is going to be hitting infinity. It's going to be negative, negative. So the way you would write these end behaviors is just basically completing the sentence. So let me show you how I'm going to do it. Grab a little sheet of paper. This keeps sliding down, so I apologize for that. So for this arrow up here, I will write as x goes to blank, f of x goes to blank. Okay, for this arrow down here, I'm going to write this. Okay, so you basically fill in the blank. This arrow means goes to, x is the variable x, f of x is the y variable. Remember, we've done that before. All right, so all you're going to do is you're going to fill those out with infinities. You just state what sign it's on the infinity. So if I'm doing this top arrow, I know that any number as that arrow goes to the up and right, it's going to be positive, positive. So your x is going to be positive. So you just put positive infinity, and your y is going to be also positive. Okay. Down here, your x is going to be negative, and so is your y. All right. Some books have it where they will write the sentence like this. Some books or programs, they will write it f of x goes to blank as x goes to blank. F of x goes to blank as x goes to blank. So basically, they've just swapped this, but you still have to know that this is the y, this is the x, that's the y. So then you would look at the y coordinate, that's positive. In this case, it doesn't matter because they're both positive, but it does matter in the other one. So I'll show you right now. Okay. So that's how you complete the end behavior. You basically just look at where the arrow, which quadrant it's on. Each quadrant has a different pairing of the x and the y signs, and all you have to do is just fill them out. Okay. All right. For the odd and negative, So let's just cover this up so that I can just start this from scratch. Up here, the end behavior will be that the x is going to the left as it's going up, right? So if I wanted to fill this out, when I give this to students on an exam, I fill it out as x, then y, just so that there's no confusion. However, a lot of books do it the other way around. So in this case, if I wanted to state the end behavior of this arrow, this would be a negative infinity, and this would be a positive infinity because that's the y. Over here, my signs are that it's positive on the x and negative on the y. We put infinities because these are obviously going to infinities, okay? And we just write it like that. Now, if it were some books in which they give you the f of x first, you still, it doesn't matter what it is. You have to know that that's the y. So you read the y first. That would be positive infinity, then the x. Over here, down here, we've got a negative infinity because that's the y, and then the x. So these will be swapped because of the order. We have negative, positive, and over here we have positive, negative because that was the y. So it depends on what the book is teaching, on how it's teaching it. It doesn't matter. You always have to be aware of who's x, who is y, and state them in that order. Okay, so that is basically how you do the end behavior. You can look at my notes, and I've written all of the end behavior here. I wouldn't want you to write this out on your note card. This is, first of all, a lot to write. Number one, look, that's already half a page, a little more than half a page. It takes up a lot of space, and it's not having you understand what you're doing. You're basically just copying stuff down and then you're mimicking it back on the computer. So before you just start putting all these down, just make yourself short, quick notes so that you understand what's going on and you can figure out the end behavior on your own. Okay, don't depend on this too much. You can depend on these two sheets that I have here for you because these are straight formulas. But these are not formulas. This is just understanding how end behavior works and what it is. All right, at the bottom of the page, and also in your lesson, hopefully you can also write these definitions down, okay? Turning points are where the function changes from increasing to decreasing. We've gone over that. So basically, you have a roller coaster. It's coming up, it hits the top, and then it comes back down. Right at that high point, that's a turning point because it's going from increasing to the point where it's now decreasing. So that high point is a turning point because it differentiates from increasing to decreasing, right? And the same thing goes the other way, that if you are decreasing and then you suddenly go up, that bottom point is a turning point. So what's the maximum number of turning points you will have? It's n minus 1. What with n? N is the degree. So if you have a 4th degree, the maximum number of turning points will be 3 because that's 4 minus 1. Okay. If you have a 5th degree, what's the maximum number of turning points that it will have? It will be 4. It will have always 1 less than the degree, and the degree is the highest power in the function. Okay. The local max is any high point, maximum, obviously. The local minimum is the lowest point. So if you have a roller coaster that has many ups and downs, like roller coasters you've gone to a Magic Mountain or any other roller coasters, if they have multiple like lows and highs, the highest of the highest will be called the absolute max. The lowest of the lowest will be an absolute min. However, all of the lows, all of the valleys, and all of the mountains will be called local max and local min. Okay. So in this case, I put the highest point or points. There might be one or many. And this one is the lowest point or points. There might be one or many. But the absolute min or max is the highest of the highest and the lowest of the lowest. Okay, so there's only one for that and one for that. Now, there could be a time where you don't have a low point. It just keeps going up and up. So you would have none. There are times where you don't have an actual absolute min or absolute max. Okay. So for this problem right here, let's see if I'm going to be doing, yeah, we're almost done with 4.1. So this is just basic information, okay? It says graph and state the end behavior, degrees, leading coefficient, turning points, local min and max, absolute min and max, domain and range, and any turning points. Okay, so the first thing we want to start is by looking at the equation, having our handy dandy calculator and plugging it in there, okay? I apologize, this is not showing. All right, this is a cubic. So for example 1, the degree is 3, which means odd. So 3 doesn't really mean much to me. Once I write the word odd, for me, it means that the arrows are going to go opposite ways. Okay, so as of right now, I don't know which one it is, but it's going to go opposite ways. If it's even, the arrows are going to go the same way. So either both up or both down. And I don't know why this moved. Okay. Then that's a 3. Leading coefficient is the number that is next to that exponent with the highest number. So if my x to the third is here, my leading coefficient is 1, and that is positive. So odds, you want to think as a line, evens, parabolas. I can't do the other one. Okay, so odd positive means a line that has a positive slope. How would it go? Well, I'm just going to draw the arrows. So that would be a line, yes, but this is not a line, this is a curve. So it just curves in the middle many, many times, right? All right, so the degree is 3, the leading coefficient is positive, and now we can look at our end behavior. So if you have a coordinate plane here, the signs for this are negative, negative, and the signs for that over there is positive, positive. So my end behavior will have 2 sentences per arrow. Well, one sentence. No, 2 sentences per arrow. I did say that right. So for this arrow down here, it's going to be x goes to blank as f of x goes to blank. That's, no, one sentence per arrow. Okay, so for this bottom one, negative. So the x goes to negative infinity, meaning left, as the y goes down. Over here on this side, you have positive infinity as it goes to positive infinity. So it goes up, it goes to the right as it goes up. Okay. All right, the number of turning points. So I'm going to put TPs. The maximum number of turning points. So if it is a degree of 3, the maximum number of turning points this can have is n minus 1, n is 3, right? So what did I do? I'm doing the answer in my head and I wrote it down beforehand. I'm sorry. I already wrote the answer. I tend to do that a lot. Okay, so it's n minus 1, and that gives us 2 turning points. That's the maximum number of turning points for a third degree. All right, so I've got degree, leading coefficient, turning points, and 1 local. Okay, so the end behavior, we've got this, we can figure out what the graph. The local min and max, absolute min and max, domain and range, turning points, we already have. The turning points are the actual points. We need to find the ones that are underlined with the graph. Okay, so I'm going to write them down, get rid of this page so we can create some space here. And I'm going to write the local min and the local max. Then I've got the absolute min and the absolute max. So the max of the max, the min of the min. All right, so we're going to have to put that in the calculator and figure out the points. Some of these will be decimal. If they are decimals, round them to the nearest 10. Don't give me a whole bunch of decimals here. Okay, 1 decimal is fine. So x cubed, why is it typing that? X cubed minus 2x squared plus x minus 2. Okay, so let's look at this graph. Okay, it doesn't quite look like that, but it does have an arrow down there and it does have an arrow going up there. So this one's a bit deceiving because I don't know what happened there. It looks like it's flat, but these are not flat at all, by the way. They are not flat at all. They look flat because it's a really tiny spring. So what you want to do is you want to make this shorter. I want to cut this right here, and I want to cut this like that. Okay, so I'm going to go to my window. I'm going to go and maybe hit -5. So I'm going to change my x min and max to 5s and my y's to 5s. So it's just going to zoom in on a 5 by 5 instead of a 10 by 10. Now it still looks like it's flat. However, trust me that none of these polynomials are flat. There's a little bit of a curve there. It's just hard to tell. So this is very deceiving, but at 2, it's kind of like that. It's just super, super zoomed out that you just see a flat line. So if you want to see basically what's going on, if you really wanted to see what's going on, you would go to zoom and we would hit box. This number 1 will actually allow you to draw a box around the part that you want to zoom in. So the cursor, I don't know where it's at. There it is. Okay, it's a little X. I'm going to take it maybe right here. And wherever I want to start the corner of a box, I hit enter. And then I go to the right. And it's literally going to make a box. Like that. And then you press enter. And now you see that it is not a line. You can clearly see that it is zoomed in so much that it is not a line. So we can see that over here, somewhere right there, okay, is a maximum. And then if I go down the curve, which doesn't, it just goes straight to the right. If I go down that curve, it is a minimum. Technically, because that curve has only one maximum and one minimum, that one maximum and that one minimum is the local max and the absolute max. So that point right there will both be the absolute max and the local max. Okay, so you don't want to guess. We are not going to guess. We are going to take this. We're going to just take the trace button. And I'm going to calculate. So you're going to hit second trace. When you hit second trace, you're going to calculate the maximum. We're going to calculate the maximum on that hill. And it's going to ask me for a left bound. So if I want this point right here, I'm going to go left of it, just a little bit left. I'm going to press enter. Then it's going to say right bound. So I'm going to go to the right of the pen. And then where it says guess, just press again. And that's going to give me the exact maximum point. Then you're not guessing. So the local max, because there's only one, that's 0.3. You can just round to the nearest tenth. And this one's -1.9. And that's both the local max and the absolute max. Because that's the highest of the highest. There's only one anyway. Okay. All right. If we go and find the minimum, we do the same thing again, second trace, and we find the minimum. We scroll to the right. Now, I want the point down here, right? So I'm going to get close to it. It's asking for a left bound. So I'm going to kind of go left of it, press enter, go to the right of, what if I do this? Go to the right, press enter, enter. And that'll give me the specific lowest of the lowest. So that's 1, -2. 1, -2. Okay. All right. We have pretty much found everything except the domain and range. All right. For the domain and range, I'm going to do them both in different forms. All right, so if you look at this kind of function, the odds do not stop going left and right or up or down. Therefore, the domain in interval notation is negative infinity to positive infinity. It's going up and down forever, so it's negative infinity to positive infinity. Okay, so it is all reals, left, right, up, down. There is no stopping this function whatsoever. Over here, if we are looking at the set builder notation, it is x bar such that, and you can just put all reals, y, all reals. Basically, the odd polynomial functions will be all reals for the most part in the domain and the range because they go left, right forever, up, down forever, because the arrows will go diagonally. Okay, they will go diagonal. And so that applies for any odd function value. Okay. All right, let's see. So for these, I would like you to practice them. We can go over them. What I ask you to do is make a quick sketch. So try to make a quick sketch without even looking at that page anymore. Just look, what's the highest power? That's a 4. That's the degree. How does that behave? It's even. Even. She told me to think of parabolas when it's even. So both arrows go up, they both go down. If it's odd, like this one, then they follow a line where the arrows go the opposite ways. Okay. So then you would make a quick sketch. The coefficient, if it's positive, what does that do? Right, to the arrows, and so on and so forth. Then you calculate, so basically you state the degree, state the leading coefficient, the maximum number of turning points, the end behavior. And then you can go ahead and find other things. If you wanted to, just to, play around with this, you can find the minimum, max, absolute, and local ones. Okay, so go ahead and try that out. This is what I have. Okay, let me erase this right here. Over down to this. Okay. Let's look at all right, so given this function, oh, I'm sorry, keep doing that. There it is. Okay, so given this function right here, find the degree, even, odd, leading coefficient, quick sketch, and here, basically exactly the same thing. The only new thing I add is the zeros. Zeros are setting this equation to 0. Now, this is not plugging in a 0 for x. This is one of the definitions I had on my practice exam. It is literally setting this entire thing to 0. 0. Now, if it's factorable, you go ahead and do it. If it's a cubic, it's hardly the case that it will be factorable. So that's where you use your calculator, right? That's what you have it for. And the absolute min and max, this is an odd. So you already know that because it's odd, domain and range are both going to be negative infinity to positive infinity, all reals. Okay, I don't want to go over that. What I want to go over is the zeros part. So let's quickly go over the information on this. All right, quick sketch. Because its degree is odd, leading coefficient is a 1, which is positive. Okay, so it's going to be acting like a line. I just have to figure out if it's a positive or negative slope. It's a positive, so it's going to act like that. So that's a quick sketch. I already found the degree. I found the leading coefficient and behavior. You know the signs. We already went over that. And I want to find the minimum, the maximum, and then the zeros. So that's where you use your calculator. Where did it go? Domain and range, I just said it, what it was. So let's go back to the window. It's obviously messed up because I zoomed in too much. So you always go to zoom and you hit number 6. And it'll always go back to the 10 by 10 by 10 by 10. Okay, so I'm going to go back to the y equals, and I'm going to erase that. Or actually, you can just write on top of it. Plus 5x squared plus 5x minus 2. Okay. And that's going to look like that. Okay, so let's make the actual sketch. So it has something like this. Okay, so you know that this is a max. That's the only max there is. So it's both the absolute and the local. Local are all the maximums. And then the absolute max is the highest of the highest, but there's only one. And this is the min. Okay. Now, so that's that. You can find those out the way I showed you. Now, what we're going to do is we're going to find the zeros. The zeros are these dots right here. It's got 3 of them. Okay. So when I look at my calculator, I'm going to basically zoom in. I don't need all this piece. It's hard to tell. So I'm going to take my zoom. I'm going to do box, and I'm going to make a big box. I want to find my zeros, right? So I don't care about how high that line is going because I'm not going to need it. What I do need is a box big enough, but not too big, so that I can see all my minimums, all my maximum, and my actual zeros. Now, do not put your cursor and guess. Please do me that favor and do not guess. You have to go to second calculate. Look at that. How beautiful that is. You don't take your cursor and be like, here, I think my minimum is, and then you just like round it. No, because again, these are such big dots that you don't know if that's that one that I have up there, the -0.6 and -0.34, -3.4. It's not exact. That was just how I placed the X. That's not necessarily true. So that's where you need to hit second calculate to give you second trace to give you the calculate button to state exactly where that point is at. So the calculator will give it to you. Don't guess. You know how to do that. Go ahead and do that. I'm going to hit trace because I want to find these zeros. So my zeros will be 1, 2, 3. I will have 1, 2, 3 points. You state them as points. You don't just put numbers that you think look like the zeros. No. So I'm going to take my cursor. I'm going to start off with that one. Okay, so I want that 0 right there. So I'm going to hit second trace and I'm going to literally put 0. I'm going to find and select the 0 function. It tells me to go left bound. That dot is already left of it. So now I'm going to go right of it. So it has to cross the x-axis, right? Because that's right of it. And I press enter again, and it gives me, now notice that sometimes it'll give you a 0, sometimes it'll give you a 1 times 10 to the, this e means times 10 to the -12. That's still 0, okay? So that's still 0. I'm gonna do -3.3, comma 0. That's a 0. The zeros are when the y equals 0. Because remember, it's like setting the whole equation equal to 0. Okay, let's do the next one. Let's do the tracing. Oops, you have to hit trace again. You have to make sure this cursor is locked into the shape. Okay, and then hit second trace to get you the calculate. Go down to 0. That's already left of my point. I want this point right here. I don't want to put my pen, but that's left of the point already. So I just hit enter. Then I'm going to go right of it. Make sure you cross the x-axis. Enter twice. And that's exactly -2, 0. Some of these will be decimals. Some of these won't be decimals. That's fine. All right, let's get the next one. And the last one, I go to trace again. Make sure that is locked into the shape. And I want to find this dot right there. So I'm going to put my cursor left of that dot right there. I'm going to hit second trace and select 0. It's already to the left of it, so I'm going to press enter. And then I'm going to go to the right of it, make sure it crosses the x-axis, press enter twice, and that should either be 0 or close to 0, which is true. So that is going to be 0.3, comma 0. And those are the zeros of my function. Okay, I already showed you how to find the minimums and the max. Now that's how to show the zeros of the function. Example 3 is exactly the same, so please go ahead and give that a try. That ends 4.1. Okay, 4.2 is a little more involved. And that's because these polynomials have all sorts of stuff to do with them, and knowing how to find their zeros algebraically is a bit rough. So let's check this out. 4.2. So 4.2 starts saying that the intermediate value theorem in a polynomial is when okay, so in the intermediate value theorem, it means that in a polynomial function for any real number a and b, if you have p of a and p of b be opposite signs, opposite values, then there is at least one real zero that was between a and b. How did that happen? What does that mean? You actually just finished doing it right now. So notice that when I'm trying to find the zeros, the intermediate value theorem says that if I try to, let me lock this in again. Let me go this way. If I put my cursor above my zero, so let's suppose I want to find that zero where it crosses the x-axis. If I put my cursor above it, notice the signs, right? This is a -2y. The y value is positive, right? So check this out. In a polynomial, the function for any real number a and b are your x values. If when you plug in a and b, so when you get the y values as the outcome, and those are opposite values, then there's at least one zero. So watch, that's a negative, that's a positive. When I go to the bottom part, doesn't matter about this number, it still it shows that this is now opposite sign. Watch, I go up, oh, sorry, not, I mean left. I go left, that's positive. So any number on the top is positive, right? Obviously, because that's the y values. But if I go below the x-axis, then they're negative. And so whenever you have a sign change, it means that you will have a zero. You will have the graph go through, it has to go through the x-axis because you had both a y that was positive and a y that was negative. And in order for you to have a y that's positive and negative, it had to have crossed through the x-axis. All right, so let's suppose it says, show that p of x has a real zero between 2 and 3. You can state it algebraically, which I will right now, and then you can show it graphically. So what do? This is a piece of cake. It's a piece of cake when you know what they're asking for. If you don't know what they're asking for, this is not a piece of cake, right? All right, so how do you show that there's a zero between 2 and 3? Well, you literally find p of 2 and p of 3. So you plug in a 2 everywhere. 2 cubed minus 2, 2 squared minus 2 plus 1. 3 cubed minus 2 times 3 squared minus 3 plus 1. And you literally do the math. Now you don't have to sit there and do this complicated math. You can just plug it in straight into the calculator. You can do 2 cubed. You can just write it all out. Minus 2, left parentheses. That's the nice thing about these fancy calculators, that you can basically do it all. Parentheses squared minus 2 plus 1. You can do the whole thing. That's a -1. And do the other one. I just hit second entry and it gave me the same function. I'm just going to go through and change the 2's to 3's. And that's a 7. Notice that these two are opposite signs. And that's enough to say that there's a zero between them. How can you show it graphically? Well, you just plug this into the calculator and you can clearly see and clearly show that between the numbers 2 and 3, it crosses the x-axis. That's how you would show that graphically. Okay, so I will let you figure that out. That's not difficult. You just graph it, look between 2 and 3, and notice that the line should go through. Whether it's crossing positively or negatively, it doesn't matter. All right. On to the next one. All right, so we're going to be taking care of long division. So this long division situation is always a hit and miss with students. Some years, some semesters, students understand it perfectly. Some semesters, it's a complicated situation for students. So it is just like a hit and miss. So hopefully it'll be a hit this time. Okay, so we'll see how that goes. Okay. All right, so let's look at the basics of division here. Okay, so back when you were in 4th grade, you were asked to divide. And so you would take some number that fit exactly into the number here or was close enough. So 4 divided into 32 gives you exactly 8. 8 times 4 is 32. You get a remainder of 0. And the way you would write this answer would just be 8. But if you wanted to write it the long way, you would write the whole number and then the remainder over the divisor. Okay, so this is a divisor. The divisor is the one outside. However, if you had a number that was like 33 and it didn't go in exactly, you would try to approach it as much as you can without going over. So you would still say that it's 8. 8 times 4 is 32. However, you have a remainder of 1, and that 1 goes over the divisor. So that's where you would get 8 and 1/4. So when you are dividing polynomials, and I'll show you how to do that, you're going to use the same idea. Not exactly, but you're going to be using the same idea of dividing and writing the answer in this format. The quotient is the polynomial. In this case, it'll be on top over here. And then you'd put the remainder over the divisor. Okay, that's how this would work. Now, when you are working with polynomial division, you will not multiply by what gets close to it. You will multiply by what is exactly that specific polynomial. You'll have to match it exactly. Okay, just to let you know, again, exactly. Okay, so let's go over this right here. Let me cover this up. Okay, so in polynomial division, answers will be written as exactly what I just stated, the quotient, the remainder of the divisor. If the remainder is 0, then you don't have to write this part, of course, because that would be 0 over something, and that's just 0. Okay, you have to make sure you account for all the powers and you put them in descending order. So that's something that I am telling you as a big hint. If you don't do that, you can still do it, but you have to know what you're doing and you have to be really good at this. So make sure that you please know what you're doing, because otherwise this won't work. Okay, so let me just move some things around. Let me move this. So many things open here. Move this up. Okay, so this is what you will be dividing. That is what you will be dividing. Let me move this here. Okay, and so how will this be written in polynomial? Okay, so where's my other page? Here it is. So let me show you how this works. You can see this, and it should be on, it should be like this already on Canvas, but I'm going to go ahead and do it again. So you place what you are dividing by, 3x cubed minus 2x plus 5. You're dividing that by x minus 3. The divisor is outside. All right, so two things. You should maybe highlight that. You're going to make sure that all the powers are accounted for. So there's a power of 3, and they're all in descending order. So I have a 3, this is a 1, and this is a 0. This is a power of 0 because there is no variable. So if there's no variable, it's a power of 0 because it doesn't exist. However, it makes the jump from 3 to 1. I'm missing a power of 2. So what I like to do, just because it's much easier for me to not make a mistake, is for me to fill in the actual piece that I'm missing. So I'm going to rewrite it again. X minus 3, 3x cubed plus 0x squared minus 2x plus 5. Okay, so now I can account for all the powers. 3, 2, 1, 0. And now when I do my division, it's less likely for me to mess up, okay? So what we want to do is we always want to look at the very first, very first term. And we're always going to match it to the first term on the inside. So the question is, what do I multiply x? So I'm going to have to put something up here. Something times x has to be exactly 3x cubed. So what times x is exactly 3x cubed? If you don't know, you grab this little piece and you divide that piece. And that'll give you the answer. That's 3x squared, right? Because that goes into that twice. So that is what I'm going to multiply x by to get this. Now notice that this is a power of 2. So I like to align things just so that I know that once I hit the last number, I'm done. Whatever is left, that's my remainder. So I'm going to take that and put it right on top of this one, just so they match. So basically I only have 2 more divisions to go. All right. Now I'm going to take my pencil, because otherwise it's going to be a mess. And I do that, and I do that. So I'm going to multiply. It's going to give me 3x cubed minus 9x squared. See, if I didn't have that, it would align down here. And I know that they're not supposed to add, but you might make the mistake and you add them. Okay. So when you are doing these, you always have to make sure that it matches exactly. Even if it had a negative, I still have to include a negative. The thing that you have to remember is to then take your pen or pencil and you literally physically subtract everything that you multiply. So that's going to change this to a minus. That's going to change this to a plus, and then you add straight down. So that's going to give me this to go away. That'll be a 9x squared, and that's going to bring this piece down. All right, I'm going to take my pencil and erase this. That's not multiplied already. All right. And you do it again. So you say, what do I multiply this by to get it to match this piece exactly? Well, I can do that on the side. I can take this number and see how many times x goes in. So that'll be 9x. That is what I'm going to multiply by. It's going to be positive 9x. Now I'm going to take my pencil, do that, and do that. So it's going to be 9x squared, which is supposed to match, which it does. And then multiply that minus 27x. Draw my line. If I add straight down the way it is, I'm going to get more x squareds. So that's not the point. The whole point is to start canceling. So I'm going to subtract. Okay. This changes that positive to a negative, and that changes to a positive. That cancels that. Where's my blue? Okay. And that gives me 25x, and bringing the next part down. Take my pencil. Erase that. And erase this. I've got one more to go because I'm missing a space right here, right above the 5. So I know it's going to be a number, right? So x times what number, or what number times x is 25x. That's going to be a positive 25. And then I go ahead and I do that. 25x, that's minus 75. And then I subtract. That changes that cancels this, and that changes that to a positive. So my remainder is 80. So the way you would write your answer, your final answer would be this top, 3x squared plus 9x plus 25, plus my remainder, I'll put it in the same color, over my divisor. Okay, and that is that. If you had a remainder of 0, you just wouldn't write it, because it would be 0. This is the longest part of this chapter, the long division. Synthetic division is easier. It's just a little complicated to understand. But it's pretty easy. We'll do one more. We'll set it up already. It'll be 5x cubed minus 6x squared minus 28x plus 8. All right, so let's see. We're going to be focusing on this piece every single time. So what times x gives me 5x cubed? Okay, you can take them and divide them by each other. Or you also can say, well, I'm already seeing what it's going to be equal to. So this into that, it's going to be 5x squared. Okay. I multiply 5x cubed plus 10x squared. I wasn't missing any powers. Okay. I didn't have to do anything there. And I subtract. That cancels, that changes this sign, and that gives me negative 16x squared, and it brings down the next number. All right, let's do this again. So what multiply times x gives me this? Exactly, it's going to be a negative 16x. I need it to be exactly, because when I subtract, it's going to be the opposite sign. So that'll be negative 16x squared minus 32x. Then I take my marker, pencil, whatever, and that's going to change that to a positive, and that's going to change that to a positive. So here, the 16s cancel, and that's going to be negative 28 plus 32, which is a 4. Oops, wrong color. And that brings this down. Okay. Last part, what can I multiply x to get it to look like exactly 4x? That's a positive 4. So then I multiply 4x, multiply, plus 8, and then I subtract. Oops. So that cancels this, that makes it negative, which also cancels, so it's a remainder of 0. So my final answer is just 5x squared minus 16x plus 4. There's no remainder, so there's no need to write the remainder like this previously. Okay. And basically, it's just practice from here on out. There's nothing more. I can do 10,000 of these, but you need to practice them yourself. Okay. As you're going through the notes, and as you see this, let's look at what this means. So let's say if in example 1, this example 1, we want to find out what's P of 3. When we have an equation, P of x equals that equation is the same as this. And I want to know what's P of 3. Well, if you want to know what's P of 3, just plug it in, right? And you end up with a number. Notice that that number is exactly the same as the remainder. Can you tell? It's exactly the same. Do you think they have some kind of correlation? Do you think that's a coincidence? Do you think that's a coincidence? I don't know. Or let's look at this one. So what happens when in example 2, we want to find P of -2? All right, plug it in. Do you think that your answer will be the remainder, just like in the other one? Check it out. Check it out for yourself. Let's see what happens. All right. So according to that, hopefully you make your findings. You can pause my recording and find out yourself. There is a remainder theorem. The remainder theorem says that if a polynomial P of X is divided by any binomial of this form, X minus K, where K is a number, the remainder is equal to P of K. And hopefully that will be true once you do this second example to prove the first one and proving the remainder theorem. So hopefully you can go ahead and prove that. Okay, so what it's saying is anytime you are dividing any polynomial, any long polynomial by something that looks like this form, X minus or plus a number, X minus or plus a number, it means that if you change the sign of that to a +3, if you plug that 3 into here, that's the same thing as the remainder down here. So right over here, if you plug in a -2 into this polynomial, you should get a remainder of 0. That's what it means. Okay? It means that this polynomial, this binomial that you see here, is a factor of this polynomial. What's the factor? Factor means it's a 0. It crosses the x-axis at that point. All right, let's do synthetic substitution. So synthetic, as you know, is fake. Okay, so synthetic substitution is a fake way to divide, but only when the divisor is in this form. So you can only use this shortcut. Yes, this is a shortcut. When you've got a binomial that is dividing, that is a divisor. Okay, so here is the equation that we had for example 1. And then I'll show you how to do that, and I'll show you how to get this out of synthetic division. Okay, I thought I had one more sheet. So this sheet is done. Okay, so let's do that specific example 1. Super easy. 3x cubed minus 2x plus 5, and you're dividing by x minus 3. Now, the key here is, like I told you from the very beginning, right here, account for all the powers and put them in descending order. That's true when you're doing long division or when you're doing fake division, synthetic substitution. You have to make sure that they are in order and descending order, and none of them are missing. If that's not true, you're not going to get the right answer. So I need to fill in this squared one because there is nothing there. And I'm dividing it by x minus 3. All right, so how do I do synthetic substitution, synthetic division, however you want to call it? You extract all these coefficients. Once these are in order, 3, 2, 1, 0, you extract them all without the variables. So you basically drop the variables. That'll be 3, 0, -2, 5. Please leave spaces. And here, what you do is you set that equal to 0, and that'll give you a 3. That 3 is going to be in this magical box. That 3 is going to be here in this box. Okay. I always draw a line at the very last number where the constant is, because this box will be my remainder. So when you are asked to divide two polynomials, you'll end up with another polynomial. Okay, so here are the steps. The first step is to drop this first number. Any number below the line will multiply with the box. So we're going to multiply with this box, and then it's going to go here. So whatever that number was, 3 times 3 is 9, and that goes here. And then these get added. 0 plus 9 is 9. This then multiplies with the box, and the answer goes here. And then I add these. That's a 25. Then I multiply with the box, 75, and then I add, and that's 80. So how do I write my answer? If I started off with the cubic, so if I started off with the 3, if you synthetically divide once, then you're going to have a squared. If you were to synthetically divide again, you would have to start with the power of 1. So I basically grab my coefficients. My remainder is 80 over the divisor. The divisor was this. Okay, and I basically start in descending order. If I started off with an x cubed, this will be an x squared, and then I go decreasing order with the ladder. That's a positive 9, x, and that's the coefficient. And that's my answer. And that matches exactly my answer here. Look at that. What a beauty. What a beauty. Okay, I'll do one more. I'll do the other example. I'll do example 2, where you had to divide, where is it? 5x cubed minus 6x squared minus 28x plus 8 by x plus 2. Okay, take this, set it to 0. In the magical box, you'll have a negative 2. You bring these down. You don't have any powers missing. That's a 5, negative 6, negative 28, and 8. And in this box, with the line right there, will be negative 2. Okay, this box will be your remainder, if any, right? So you start by dropping the first number and you multiply by what's in the box and write the result there. I'm going to put multiplication. So that's a negative 10. It's going to be negative 16. You multiply with the box. That's 32. And these you're going to always add. That's a 4. Multiply with the box. Negative 8. Remainder of 0. You started off with the cubic. When you write your polynomial, that'll be a squared. 5x squared minus 16x plus your constant. Done. There's no remainder. That was exactly the same answer that I ended up with when doing the long division. All right. So the other parts are questions that I need you to answer and just think about. Okay. And then we have the factor theorem. So the factor theorem, these questions are for you to answer. All right. The factor theorem is basically what I just finished doing. Factor theorem is if a polynomial p of x has a factor of x minus k, and you end up with a remainder of 0, it means that that binomial was a factor. It means that it evenly goes into that polynomial. Okay, if you're like synthetically dividing or just long division, it means that it goes in evenly, completely, utterly even. Okay, there's no remainder. So let's say determine whether the specified binomial is a factor or not. So what you would do is, you can do it 2 ways. You can do this in the long traditional way, in which you plug in this number. So the opposite of that number, if you have it in a binomial form, you plug it in and you end up with the 0. That means that your remainder was 0. That means that it is a factor. Okay. Or you can use the synthetic division. You can pull these numbers out. Now notice I hear you're missing a cubic. 4, 3, 2, 1. So you're just missing a cubic. So you do have to fill it in with the cubic if you're using synthetic division. And you would plug in a 1 into that magical box and see if the remainder is 0. If it's a 0, it means it is a factor. So for this example that we just finished doing, it means that this is a factor of this polynomial. Graphically, what does it mean to be a factor? It means that it is an x-intercept. So if I were to graph this polynomial, which I ask you to do so, please go ahead and do so. You will notice that one of the, it could have many x-intercepts, but it has, I know for sure, an x-intercept at negative 2. There's an x-intercept at negative 2. That's because the remainder cannot be 0. So that's what the factor theorem says, that if your remainder is 0, that was a factor, meaning that is an x-intercept. That's what all this means, and it all kind of comes together. Okay, so please check this out. Finish that off. Okay, so it's the same thing. This is just some more practice. You can do this long division. You can do this synthetically whenever you can. In this case, you cannot do this one synthetically. You cannot do this one synthetically. I repeat, you cannot do this synthetically because the denominator is not in x minus a number. It has x squared, and that's not the same. Okay. All right, here you've got some more practices. It says use substitution to determine if the given number is a 0. If they just give you the number, then just plug in that number. Notice I didn't change the sign. If they give you a number, just plug in that number. However, if you're given a binomial, you have to set it to 0, and you have to you end up plugging in the opposite of that number, right? Okay, so make sure you know the difference. And then can you check if your long division or your work answer are correct? How can you check? Okay. According to what we've done, how can you check? All right, so we've gone over long division, we've gone over synthetic division. So please go ahead and do the problems that I have up there. Okay, let's start with this. In synthetic division, when the remainder is 0, which I already stated, this means that there is a 0 or an x-intercept at that number. So if I take this polynomial, I put the coefficients, I plug in a 2, and I ended up with a 0, that means that yes, 2 is an x-intercept. So 2, 0 is a point on the graph, and it is the x-intercept, one of the x-intercepts. If I ask you to do this one and test it for 4, and you go ahead and you test it, and I don't end up with a 0, it means it is not a 0. It just means that 4, 2 is a dot on the graph, but it's just a random dot that is not on the x-axis. If it is on the x-axis, the y has to be 0. Remember, this is your x, this is your y. This is your x, and whatever is the remainder is technically your y that gets paired with that x. Okay? Wrote it down here. So P of 4 equals 2 is just a point on the graph, but it's not an x-intercept. Okay? Synthetic division is helpful in finding all the zeros of a polynomial by reducing the powers. So remember how when you divided by one specific number, and then we wrote down the polynomial function. I started off with the third degree, and when I wrote it down, I started off with a 2. That's how you can find the rest of the zeros, because every time I divide by a specific, by a number, it starts reducing the power. So that's one way, and I'll show you how we're going to use that in a minute. Okay, so this is just more examples. You can finish those and check those out. Now, this is 4.3, and I'm going to now pause the video because it's just going to take much longer. So I'm going to pause it here, and then I'll do one for 4.3, 4.4. I'm going to stop sharing and pause the video.